Alright, for those of you who are saying and being very smart and realizing, hey, you know what? Wind, current, things like that don't always go in the exact same direction you're traveling or the exact opposite direction you're traveling. Things do come at you from a side. So this is what this will teach you about. So, right angles, we're going to work with right angles just because that makes easy triangle math. So let's say we have a motion of an object, say a plane flying east. And that plane encounters some wind, but that wind is blowing north. Alright, so what's happening is, say you're observing the flight of the plane, or just in general, you're trying to get the plane from, say, Phoenix to Chicago, but you have to factor in winds and things like that, right? So what we need to know is how the plane is actually moving in relativeness to the Earth, so that we can get it to its correct destination. So what we know is its resultant, all right? It's relative motion. So whatever this resultant dotted line velocity would be, okay? So we're going to be working with these three parts of motion and how they relate to each other, what information we can get from them, all right? So we're going to start out easy. Let's just figure out the plane's relative velocity, all right? So we have a plane flying south at 100 kilometers per hour. Sounds familiar. So here's our south at 100 kilometers per hour. But we have a crosswind, 100 kilometers per hour south. A crosswind of 25 kilometers per hour to the west. Which is going to be to the left, so I'm going to draw that up here. 25 kilometers per hour west. Alright, we want to know what's the plane's velocity relative to the ground. Alright, so what we need to know is this line, our resultant velocity, which goes from the open tail to the open head. So we want to know this one. Alright, so again, Pythagorean theorem. If you don't know it by now, hopefully the third time we use it for something, this will make it click. Alright. So we're going to have 100 squared plus 25 squared, don't need that, 25 squared equals our c squared, which is our c is what our velocity is going to end up being. So that is 100 squared is going to be 1, 2, 3, 4, 10,000 plus 25 squared, which is 25 times 25, 625, equals c squared, or 10,625 equals c squared. So we need the square root of 10,625, which is 103 kilometers per hour. What am I missing? Hopefully you are saying direction, and that should be southwest. Alright? So, let's apply this to another situation where you might run into these sorts of things. And those are riverboat problems. So we're going to do some practice with these, because riverboat problems tend to make things a little more complicated. Alright, so let's, again, pictures come in really handy. So we have a motorboat, and I'm going to, let's see, here's our shore, here's our river. And we have a boat. Okay, our boat is going 3 meters per second east. That should be an S. Alright. And then we have our water going north at 2 meters per second. Okay. So, first question is, what is the resultant velocity? That's the easy part. That's just taking our two vectors and finding their resultant. Alright, so for A, we're going to have 3 squared plus 2 squared equals c squared, or 9 plus 4 equals c squared, or 13 is equal to c squared, and c equals the square root of 13, which is 3.6. So that's 3.6 meters per second, and then hopefully you are saying northeast. Okay? Now we're going to get into tricky stuff. So let me write this here. 3 meters per second northeast. So we have that one. I'm going to erase this down here so we have some more room. So the next question is asking about if the width of the river is 80 meters. Alright, so our river width is 80 meters. How much time does it take the boat to travel to the shore? Alright, so the hard part to these sorts of problems is knowing which velocity to use where. So if you think about your boat, and if your boat started down here, in 1 second, it's going to be, say, about here. And what's literally happening in that 1 second, the boat itself is moving like this. To someone standing on the shore, it's literally moving in a diagonal line. But that diagonal line comes from our triangle, with the 2 meters up and the 3 meters over. Every single second, the boat will still move 3 meters per second to the east. It's just simultaneously, it's also moving with the current 2 meters per second north. Alright, so those movements happen together. The relative motion is the fact that you see them happening together. You don't see them happening separately, but they are occurring. So when we want to talk about the fact that we need to go 80 meters across the shore, we need to use that velocity that is actually moving the boat across the shore. Okay? So in order to find this, our LESU for this problem would be our velocity is going to be the 3 meters per second east, because that's what's literally moving the boat from one shore to the other. Alright? The current is not helping the boat get across the river. It's moving it downstream of the river. Okay? So the only portion of this triangle that is helping get the boat across is the motion across the river. Okay? So in order to do that, then we also know that our displacement is going to be 80 meters. Alright? And we want to know time. So our equation is going to be V equals displacement divided by time, which is, and time equals displacement divided by velocity. So if we plug things in, we're going to have 80 meters divided by 3 meters per second. 80 divided by 3, and it's going to take 26.7 seconds to get across the shore. Okay? Once you figured out time once, that's the same amount of time for any other motion that occurs. Because once the boat gets from one shore to the other shore, it's done. Movement's over. So time is over. There's only one time you have to deal with riverboat problems. The tricky thing is that there's multiple velocities you have to deal with. Okay? So now the next question is, what distance downshore or downstream does the boat reach the opposite shore? All right, so this is talking about, let's see, I want to erase some stuff so that we're not getting too confusing. So this is talking about not the distance across, but this time if we start down here and say the boat ends up here, is this distance up and down. The boat starts at this point and ends at this height on the river. We can ignore the fact that it moved across, okay? And what speed is literally moving the boat downstream? Hopefully you're picking up on my color coding and my arrows and things like that. It's the current. The current moves the boat downstream. The boat moves it across the river, okay? So if we think about this being point A and this being point B, we want to find just the height difference, the stream distance between A and B. So essentially this distance. We can ignore the fact that it's moving across the river. All right? So to do this, you have your velocity being the 2 meters per second. Okay? Your, jump the gun here. Your time we solved in the problem before being 26.7 seconds, right? And what we want to know is our displacement. So our equation, velocity is equal to displacement divided by time. Displacement is equal to our velocity times time. So that's going to be 2 meters per second times 26.7 seconds. And that ends up being 53.3. And your units should be meters. Now, be careful. We are solving for displacement, so what else do we need? You need to know your direction, and it's moving north. Because literally, it's moving it 53.3 meters north downstream. Yes, streams do travel north. It's not very common, but there are rivers that flow north. And last part. This is where your gut reaction for all of these other problems is to use that new resultant velocity for everything. Part D is when you get to use the resultant velocity because you want to know the total distance the boat travels. All right? So let's, 53.3 meters. Go back to erasing. Part Sorry, having technical issues here. Why aren't you erasing? Let's see, I'm just going to move this over. So this time, we are trying to find out if our boat starts here and ends here. We want to know this distance. Alright? It's total distance traveled, and that is actually going to be represented of the actual motion of the boat. Okay? So that means for this, if we do lasso, our velocity is that relative velocity that we figured out, which was 3.6. meters per second northeast. Alright? Our time is still going to be 26.7 seconds because if you think about this trip, the green arrow of distance is made up of the arrows that we used to figure out the other two. Alright, so all of those arrows take 26.7 seconds. And our equation, v equals change in s over t. And this time we want, again, we're finding a distance, so change in s equals velocity times time. So we're going to have 3.6 meters per second northeast times the 26.7 seconds, which is 96.1, and our units will be meters. And this time, what is our direction? Because our arrow is actually on the angle, we have the northeast direction. Okay? So, this is a little tricky. The big things to remember is that the speed of the boat determines how you get across from shore to shore. How you get from one side to the other side of the river. The speed of the water determines how far downstream you end up going. And then your resultant velocity is what gives you the total distance that you actually travel. Because that's what your path actually looks like. But this green path is made up of the other two. Okay? Please bring questions to class if you have them. And I will see you in class tomorrow.